Hey guys, guess what? You made it. This is the last set of trig function or derivative rules that you will learn. We're going to talk today about inverse trig functions. Up until now, we've done every other function that we will need the derivative for, so today is the last day, which is exciting news. So we should have all those things memorized or working on getting memorized. Today we have 6 more trig functions, inverse trig functions, derivatives to know and memorize, but after that everything will end up being done. So for our warm-up, before we actually get started on that, this is just an application problem that I think I got off of a free response question for an AP test or something along the line. So our question today is show that this curve that we have, y equals negative 1/2 x squared plus k, is always orthogonal to this other curve, y equals natural log of x plus c. So what that means, if we're thinking about how to approach this problem, orthogonal means that it's always perpendicular. So if I was thinking about something being perpendicular to something else, what I should be thinking about is slope. So let's take these two curves. So I'm going to call like this curve number 1 and this curve number 2. So if I was thinking about these two curves and I found the derivative of my first curve, I would end up having to do the power rule. So this k, remember that I have, is just some constant. So when I take the derivative of that constant, that's just going to go away. So if I take the derivative of this piece that I have first and apply the power rule, the 2 would come down, it'd cancel out with that 1/2, so I'd end up getting the answer of negative x. And if I found the derivative of my second function, so this is function number 1, I'll find the derivative of function number 2. If I was finding the derivative of this piece, derivative of natural log, we just did that last lesson, so derivative of natural log is 1 over x. And then that plus c that I have is just a constant, so that'll go away too as 0. So looking at what I have, negative x and 1 over x, these two curves, negative x and 1 over x, are always opposite and reciprocal slopes. So that means that they are always orthogonal. So we just kind of proved and showed that that was true. Okay, so leaving that aside, we're going to talk about the derivative of our inverse functions. So we're going to start with y equals sine inverse of x. And again, like last time, we actually proved the derivative of natural log. So we're going to do that same thing here. We're going to prove the derivative of inverse sine. So to do that, since I don't know what the derivative of inverse sine is, I'm going to end up taking this function and make it look a little bit different than what it is now. So last time we said, okay, well, I know that natural log and e to the x are inverses of each other, and so I know how to find the derivative of e to the x, so I can use that for the natural log. Same thing here. I know that sine x and inverse sine are inverses of each other, so instead of writing it this way, I'm going to write it as, or if I take the sine of both sides, I'd end up with sine y equals x. So sine of sine inverse ends up just canceling out. So these are equivalent functions, they just look a little bit differently. And so now since I'm finding the derivative, I can take the derivative of this side. I'd have to take the derivative again implicitly because I don't have an exponent or a explicit function. So if I do that, the derivative of sine is cosine of the inside piece times dy dx equals the derivative of x is just 1. So I end up with dy dx is 1 over cosine of y. And last time, again, what we ended up doing is we said, well, since we were given some explicit function in terms of x, we should end up with some explicit function in terms of x, or explicit derivative, I should say. So now I have to back substitute. So I get 1 over cosine of sine inverse of x. Now that's pretty ugly. I don't actually want to leave it like that because cosine of sine inverse is something that I can simplify a little bit. So to do that, I'm going to start with kind of what this meant originally. So what this really means originally is if I'm saying that y so like looking at my original function, what I have here is that y is some angle, because that's what inverses help me find, is some angle y. So that's what I have here in the corner of my triangle. And this ends up being a ratio of two sides. So if I was dealing with sine is opposite over hypotenuse. So that means that from this angle, my ratio is x over 1. So opposite is x, and my hypotenuse is 1. So my other side of my triangle of my Pythagorean theorem, I'd end up getting 1 minus, 1 minus x squared. Okay, so now what I'm actually finding is cosine of y, so cosine of this angle. So if I go back to my triangle, my little reference triangle, cosine is adjacent over hypotenuse, which means that my this whole thing evaluated is really just 1 over square root of 1 minus x squared. Now you don't need to know the actual evaluation of, or the derivation of the inverse trig derivative, but I wanted to show you that because when I give you all the inverse trig derivatives here in a second, I didn't want you to be like, what the heck, where do those things come from? So it actually comes from reference triangles and that kind of idea, and you could do the same thing with all the other ones. We won't, but here they all are. So like take a minute and write all these down, because I don't want to.
On.
Hi.
Hi.
So I just want to, like, as you're writing these down, and if you paused and wrote them down, you actually don't, even though we have 6 derivatives that we have to actually, memorize still, we only have really 3. So if you notice, these are like almost identical. The only difference that we have with, these are kind of cofunctions and cofunctions and cofunctions. So we have a pair of cofunctions that have really almost identical derivatives. The only difference is that this entire side here is all negative. And so one way to remember this is that like all the functions with c here are going to end up being some negative thing. And that happens with derivatives too. Like the derivative of cosine is negative sine. The derivative of cosecant is negative cosecant times cotangent. Derivative of cotangent is negative cosecant squared. So that should be easy to remember for the future. So the hard part of today is not actually taking the derivative piece. The hard part of today is actually going to be the simplification of that. So I'm going to start with my first example of secant inverse of 5x. And so the easy part is just knowing, and right now you don't have it memorized, so you can use obviously your notes to come up with this answer. But the easy part is actually like finding then the derivative of secant, which is given to you. This also is a chain rule because we have the derivative of 5x that we have to deal with as well. So let's start with the outside function. So the secant derivative is 1 over absolute value of x. Our x is going to be 5x in this case. So 1 over an absolute value of 5x. And the square root of x squared minus 1. So that would be square root of 5x squared minus 1. But again, this all gets multiplied by the chain rule. So the derivative of 5x is just 5. Oops, not 5x, just 5. And then we can do a little bit of simplification. So one thing that you'll see when you're doing your homework in your book is that like these 5s will end up canceling out actually, but they'll rewrite it in your book a little bit different. So if you know already that x is positive, they'll end up dropping the absolute values. So know that that's also the case too. Like they might pull that 5 out already because 5 is positive. It doesn't need to have the absolute value of that, and we might just have the absolute value of x. So that's what I'm going to write first. And then the inside part of this radical will be 25x squared, and then we multiply by 5, so I should have a 5 in the numerator. So these 5s will end up canceling and out from the numerator and the denominator. So we'll get that as our final answer here. So that one's not too bad. The simplification was not a terrible simplification. The next couple that we deal with will end up being a little bit more complicated. So here's our next one, inverse cosecant of x over 2. So again, we've got obviously some chain rule situations. We've got this derivative, and we end up having the second function of x over 2. So this, by the way, is like 1/2 x. That's another way to write it. So actually a really simple derivative that we're going to deal with. But again, the actual derivative portion of this is not hard. It's the simplification that will end up being a little bit tricky. Okay, so derivative of cosecant is just like the derivative of secant that we have above. The only difference is this is a negative. So we already did kind of something like that. We'll have -1 over the absolute value of x over 2 square root of x over 2 squared minus 1. And then we multiply by that the derivative of the inside function. So my inside function is x over 2. The derivative of x over 2, or derivative of 1/2 x, is just 1/2. Okay, so let's do a little bit of simplification. I already know from this problem above that these 5's will end up canceling. So these 1/2's will end up canceling too, so I'm not even going to bother to write that. So I do have the absolute value of x here in the denominator. And I have, if I simplify this inside portion, I'll have x squared over 4 minus 1. So I don't want to leave it like that because I've got fractions within fractions, or at least the book won't leave it like that. I don't really care if you left it like that on a free response question, but multiple choice questions won't be written like that, and your answers in the book won't be written like that. So we do need to be able to do this next step to simplify. So because I have fractions within fractions, I'm going to start here with this radical, and I'm going to combine that into one fraction. So I'm going to find a common denominator, which is 4. Oops, -1 over. So I'd end up with the square root of x squared minus 4 over 4 if I found that common denominator and simplified that. So I can now take the square root of the top and the square root of the bottom. So I'd get the square root of x squared minus 4 over 2. And then last but not least, I could multiply by the reciprocal and move that 2 up to the numerator to give my final answer that's much more simplified than my original answer was of -2 over absolute value of x times x squared minus 4. Again, the actual doing of this problem, this first step is not hard. It's to get to this step that's a little bit harder, and always be the same thing. It'll always be find this common denominator, and then this will be some squared, so you can actually end up taking the square root of it and simplify from there. So let's do one more like that, where we're doing a little bit more complicated version. So we're dealing with inverse sine. Again, two different functions here, obviously, inverse sine, and we have 3 over x squared. So this one I'm going to rewrite just for my sake later as 3 x to the -2nd power, so I can find the chain rule or use the chain rule a little bit easier. So the derivative of arcsine is 1 over the square root of 1 minus x squared, and in this case, again, that x value that we're dealing with is this whole quantity, so 1 over 1 minus 3 over x squared quantity squared. And then again, what we have to do is multiply by the derivative of the inside function for chain rule. So the derivative of 3x to the -2nd power, we would bring down the -2 and make that -6, 3 times -2, and then x to the reduced power by 1, -3rd power. So again, that's not the hard part. The hard part is actually the simplification version after that. So like I said, in this problem, we've got fractions within fractions, so we know we're going to end up having to find a common denominator. So in this case, my common denominator, this will end up being 9 over x to the 4th. So I'll have x to the 4th as my common denominator, so I can change this 1 as x to the 4th over x to the 4th. So my top here would be x to the 4th minus 9 over x to the 4th. And I'll rewrite that part as -6 over x cubed. So likewise, if I take the square root of the top and the bottom, this will be over x squared. So the square will end up being 1 over square root of x to the 4th minus 9, all over x squared. And when I multiply by the reciprocal, that x squared will end up appearing in the numerator. And now we can simplify a little bit. So these x squared will cancel with 2 of those. So you'll end up with the final answer of negative 6 over x square root of x to the fourth minus 9, excuse me. Again, that's the hard part, is all the simplification that goes along with it. And so you'll see that in your homework too. Like, this will be the answer that they end up giving. And so you just have to make sure you can get to that point. Okay, last example for today. Since we haven't done one with tangent or cotangent yet, let's do one of those. Cotangent and tangent, so of all the ones that were listed on the previous page, all of the trig identities, or sorry, the trig derivatives, tangent and cotangent are going to be the ones, actually tangent most likely will be the one that comes up most often. So that one's like extra important. Everything else obviously you should know, but tangent is the one that is the most commonly used on either in your book or on AP tests. It's just because like these functions, I'll go back real quick so I can talk about it. I meant to say it when we were talking about it originally, but I forgot. So these functions don't come up really often, but 1 over 1 plus x squared is relatively like a simple function. So like because of the simplicity of what that looks like versus something like this does actually appear more often, and it'll especially be more prevalent when we talk about our integral unit next unit. So, or 2 units from now, unit 3, when we talk about integrals, that function appears a lot. So that's going to be one that you're going to want to remember. Okay. So the derivative, again, this is like a couple different things. We've got chain rule happening because we've got an outside function and an inside function. So I'm going to handle the outside function first, cotangent inverse. The derivative would be negative 1 over 1 plus the x value squared, which in this case our x value is square root of x minus 1. So that quantity squared, and then we have to take the derivative of our inside function, which if I write that as x minus 1 to the 1/2 power, that makes it a little bit easier to see that derivative. So power rule tells me I'd bring down the 1/2, I'd reduce the power by 1, and then I'd actually multiply by the derivative of the inside function in this case, because it is 3 actually different functions, cotangent, square root, and the inside of that part. But that derivative will just be 1, so I'm just going to leave it alone. If I simplify a little bit on this one, when I square this, the square and the square root will cancel. I'll have 1 plus x minus 1, so the 1's will go away. So on that section, I'll be left with negative 1 over x. And this I can write as 1 over 2 root x minus 1. So overall, I get something that looks like that. So again, once again, the actual applying the derivative is not super complicated. It's just really the simplification. That's the hard part for this lesson.